All right, welcome back, everybody. We've got our second Dan of the day. We've got Dan Boley here to talk a little bit about machine learning methods. So thank you, Dan, for being here, and go ahead.
Well, thank you, Kevin, for inviting me to give a talk to your class. I'm Dan Boley. I've been here a professor in the computer science department for over 30 years, after which I've stopped counting. I work generally in more mathematical, numerical linear algebra to be specific. But I've also dabbled in areas where you can apply some linear algebra, and one of the areas is machine learning. I occasionally teach the class Introduction to Machine Learning, and so I thought, I didn't know the background of you folks, so I thought I would give what basically amounts to my introductory lecture in this class, which is basically a quick run through of a lot of the methods that we talk about in that class. I have to say machine learning and AI is a big area, so I can just sort of scratch the surface here. So let me get started. I'll say a few words or spend some time on classical methods that are still useful in a lot of ways in machine learning. Illustrate a couple of deep learning methods, and illustrate everything with, I'll be using some small toy examples to illustrate all of the methods. I'm trying to keep the mathematics to a minimum. In fact, I don't think I have a single equation in this talk. So I'm going to be using my toy example to illustrate everything. I'm not sure what the protocol has been in your class, but I guess you can just pipe up and holler if you have a question. I don't mind. In fact, I welcome interruptions. Machine learning machine learning methods in general can be divided into supervised methods and unsupervised methods, depending on whether you have labeled data. I should preface this that hopefully will be of interest to you. So in any case, what you generally think of as machine learning involves labeled data. So the standard process is that you're given a set of data with some ground truth labels, like you're trying to classify, like in one project I'm working on, we're looking at chest x-rays, and we want to say something about whether the patient has COVID or not based on the amount of fluid in the lungs. And so we have a lot of images, and for each image we have a yes and a no, and we would try to design a machine learning algorithm that could look at this picture and make a prediction. Is this yes or a no? And then we can compare it with the ground truth. And that's the supervised method, and that's what most people think of as the standard machine learning process. But there are a lot of cases where you don't have labeled data. You have a lot of data but not labeled, because labeling the data requires somebody to look at it and actually assign labels. So it could be expensive to obtain labeled data, whereas one might be able to obtain a lot of unlabeled data. And so unsupervised methods also play a big role in machine learning. I'll spend most of the time here talking about supervised methods and say something about, give some examples of unsupervised method at the end. The unsupervised methods come under different categories. One is to try to find patterns or groupings that are hidden in high dimensional data. And the other one is to try to reduce the dimensionality. So a lot of data that you get is tabular data. So you might have like images. For each image, you have all the pixels. So you just lay them out in a row. And so if you have a 28 by 28 image, that would be a vector of length 28 squared, just laid out, and that's your input data. And then you have a label attached to it, which could be a 1 or a 0. And that's kind of high dimensional. So one of the things that one would like to do is reduce the dimensionality. So let me start with my toy example. So suppose you have a collection of fishes and you would like to design a vision system that would distinguish salmon from sea bass. This is sort of a prototype that I learned when I first took a course in machine learning. And from the image, you extract two features. You extract the width of the fish, and you extract the brightness or lightness of the fish image. And you can plot. So each fish is reduced to a two-dimensional feature vector. The blues are, I guess, the salmon, and the reds are sea bass. And you would like to be able to design a machine learning algorithm that would distinguish the salmon from the sea bass. So the various methods that can be used. So one thing that one would like to do is to see if how much of the information that's contained in this image, in this set of data, has to be preserved so you can design a machine learning algorithm. So one obvious thing is to look at this picture and see, well, suppose I just look at lightness. So you just draw a cross section along the horizontal image of along the horizontal axis here. That actually doesn't do a half bad job. So if you ignore the width, you can actually do a pretty good job in distinguishing the fish. Whereas if you just look at width along the vertical axis, it doesn't look like it works as well. So if you draw the histogram of this, you would see that with lightness, you can get a pretty good separation between the categories, but with width, it doesn't work as well. And all of these smaller bars here represent the probability of an error. So you can actually measure, one of the things you want to do is measure what's the probability that you would make an erroneous classification. And that would be represented by the shorter bars in this picture. In order to draw this picture, I have to record all the fishes. So if I have like 150 fishes in this data set, I would have to remember all 150 data samples in order to draw this histogram. If you don't want to remember so much, I mean, especially if your data set is not only 150, but if it was several thousand or 1 million samples, you don't want to have to remember all of them. Can you sort of encapsulate all the data into a few numbers that would sort of represent all your data? And that is called the parametric method. Instead of remembering all of the data, you reduce it to a few parameters that sort of give you an approximation of how the data is distributed. And the simplest one is to compute the mean and variance of each class. So you have two curves here. The blue curve gives you the sort of the bell curve that fits the salmon, and the red curve gives you a bell curve that fits the sea bass. And in this one-dimensional case, you reduce your entire data set to 4 numbers: the mean for salmon, the mean for sea bass, the standard deviation for salmon, and the standard deviation for sea bass. And with these 4 numbers, then you could, given a lightness figure like 5, you could decide, well, the probability is it's more likely that this fish is a salmon. This may not give you a very good classification, but at least it's better than totally random. And obviously with the width, these two curves are much closer together, less well separated. Obviously, doing in one dimension is not as good as keeping both dimensions at once. So you can try to fit a sort of the mean in 2 dimensions. So now the mean is a 2-dimensional vector. One mean is over here in the center of the blue circles, and the other mean is over here in the center of the red circles. And you try to record also the variance or the standard deviation, how spread out these fishes are. And there are various ways of recording the variance. In this particular picture, we assume that the variance is isotropic in all directions. And so we can record one common number that applies to both fishes at once. So there's only one number. This sigma is just a single number that applies to both classes at once. And then the separator is a straight line, which is this straight line here. Everything to the left would be classed as salmon. Everything to the right would be classed as sea bass. And you can tell that there are some mistakes. There's some red crosses on the left, and there's some blue X's on the right. Not very many, but there are a few. You can generalize this to a more general covariance matrix, which in this case would be a 2x2 matrix that gives you, allows you to model data that is not uniformly distributed in all directions, but is more spread out, say, in one direction, as opposed to the other direction. So this is more spread out in this, as you go vertical in this direction, sort of along the width, than it is if you go along the lightness. And in order to simplify matters, in this particular case, we use this picture shows the case where you assume that the two classes both have the same covariance matrix. If you use a common covariance matrix, then you can guarantee that you have a straight line separator. If you allow the covariance to be different on each side, then the separator becomes slightly more general. Here you can see it's curved. This separator line is curved, and in fact it should be a quadratic. So this allows slightly more flexibility in the separator, but at the cost of keeping more numbers associated with the data. So this gives you an idea of what happens if you use a purely probabilistic analysis, try to fit Gaussians to each Gaussian probability distribution to each data set. So the assumption is that this data represents the distribution of future fishes. So if I use this as a training data, then my future fish, when I start using it on new catches of fish, presumably it'll be in a different location. So it could be here where the arrow is, and I would have to classify it. And if it's close to the boundary, it may not give me a very reliable classification. That is, the probability of error could be substantial. And if I use probability distribution to model each class, this actually does yield a probability of making a mistake, assuming that the future fishes also follow this Gaussian. I'm not going to go through the math, but if you use a probabilistic model here, it would give you a prediction on the probability of making a mistake. This is that was an example of a parametric type of classifier where you reduce the data to a few parameters. This is a model. This is a method which is non-parametric. It's called nearest neighbor, and it's probably the simplest conceptually. So if you pick a point, say at where this arrow is, and you want to know whether my fish is a salmon or a sea bass, what you do is you just look at your in this case, three nearest neighbors, which is an X, and a plus. Well, with two X's and one plus, you vote and decide that I should be an X or a salmon. And for each point in the domain, you'd simply look at the 3 nearest neighbors and take a vote. And in order to do this, this is called non-parametric, because in order to carry out this classifier, it's very simple conceptually, but it does require that you keep all the training examples at hand, because you could get new fishes that could be anywhere in this domain. And so you have to be able to retrieve the 3 nearest neighbors, which could be any of these 150 odd fishes. This doesn't give you any kind of probabilistic interpretation of a probability of making an error. And you can also see that the boundary between the fishes can be very irregular. And this is actually a sign that this is probably going to be suffer overfitting. You can also see that even though this makes fewer mistakes on this training set than the previous method, there are still some red pluses on the wrong side and even a few blue crosses on the wrong side. At least 2, 3. So this, of course, the choice of 3 is somewhat arbitrary. I could try to see what happens if I use more than 3 neighbors. You almost always use an odd number of neighbors to avoid ties. If you use 5, you get a very different curve. And if you use 9, I think it's slightly smoother, but it's still very rough around the boundary. So this is a method that is used because of its simplicity, but it's not really used a lot. Unless what people usually do is try to smooth this out. So instead of taking a vote of the 3 nearest training points, you sort of imagine that each training point has a force field around it, and you weight the votes by how far you are. And any point that is farther away than some threshold, you decide to ignore. So suppose you look at, so you could think of taking every point, you draw a circle around every point, and anything outside the circle you ignore, and anything inside the circle you weight by the distance from yourself to the point. And that gives you sort of a smooth version of, let's see, I had a smooth version of the nearest neighbor, which is basically this Parson window technique. And if you use a Parson window with very wide fields, you get a rather smooth separator, which can do a better job in separating the points. This is not really, this is really non-parametric, because you still have to save the entire data set in order to draw these sort of force fields. You can think of it as a smell test. So if each salmon puts out an odor that smells like a salmon, and each sea bass puts out an odor that smells like a sea bass, then at any particular point you can sort of nose the air and sample the air, and if you have a greater smell of sea bass, then you classify this position as a sea bass. And any smell, and the smell particles only travel a limited distance, and they also dissipate quite rapidly. In this particular case, they're not dissipating that rapidly, but if I skip to the next slide, this is what happens if you have them the smell dissipating very rapidly. You get a lot of areas which probably are not well differentiated at all. So in this particular case, since I think the sea bass is slightly more numerous than the salmon area is closed and the sea bass area is open. This often, if you use a wide area, slow dissipation, then you can get rather smooth, non-linear separators that can actually do quite a good job. I skipped this one other method, which dates back to the 1930s, actually, called Fisher's linear discriminant. And that is to find a single dimension that would do as good a separation as possible. So at the beginning picture, I said that if you use the horizontal axis, that would give you a pretty good separation. Whereas if you use the vertical axis, it would use very poor separation. So if you pick an angle like this, that would actually give you a better separation in either axis alone. And there's a statistical method here for determining this particular direction, which in this particular case, you want to maximize the separation between the two means, the two centers for the salmon class and the center for the sea bass class, while at the same time minimize the scatter within each class. The scatter within each class is basically the sum of squares of the distances from the mean of that class to all its samples. So if the mean is here, you take the distance from this mean to every single sample, you add up all those distances, and that's the item you want to minimize. And that turns into actually a nice linear algebra problem, an eigenvalue problem that one has to solve. So that's an example of using a parametric or non-parametric method to get a separator that tries to minimize the a measure of the error. That is the number, it's not quite the number of misclassifications, but it's some measure of the number of misclassifications where the distance to the boundary is, the error is weighted by the distance to the boundary. So in most of these cases, the error that counts from a point that's close to the boundary would count less than the error induced by an erroneous classification that's far from the boundary. The other classical machine learning method that's still used quite a bit because it tends to be very robust is what's called a support vector machine. And the support vector machine is basically a classifier which tries to separate the red points from the blue points by finding a strip of no man's land between them in which there are as few cases as possible. And the optimization problem is to balance the number of points here in the middle and to minimize that while maximizing the width of this no man's land. You can think of trying to put in a separator that instead of being a thin line or a thin hyperplane in high dimensional space, it's a thick beam, and you want to make it as thick as possible because the wider the separator is, the more robust is the classification. And in the case of items that are linearly separable, you can actually find a straight line that would put all the red points on one side and all the blue points on the other. You would like to not only find a separator, but one that is as wide as possible. The support vector machine in the linear case, you actually try to find straight line separators. And of course, with this particular data, it's impossible to find straight line separators. But you can find one where you allow a certain number of errors. So in this picture, the crosses and X's that have no circle around them are correctly classified. And everything that has either a box or a circle around it is incorrectly classified or is fuzzy. Anything in the middle of this no man's land is sort of fuzzily classified. And the big crosses, this one has a big square, this one has a big square, and this one has a big square around it. Those are the 3 points that determine the orientation and width of this no man's land. All the other ones are sort of just treated as errors or bounded support vectors. So in this particular case, there are 3 regular support vectors that determine the width and orientation of this no man's land. And then there are these what are called bounded support vectors that are the fuzzy ones. And of course, here you have a parameter to remember. Here I'm trying to minimize the number of errors while maximizing the width of this no man's land. And you have to weight these 2 competing goals. This one is one where I'm trying to really make the number of errors as small as possible, but you can relax that by changing this one parameter. And I believe the next one shows what happens if you relax it. This makes the beam a little wider, but allows for more errors in the within no man's land. And if you make it even more relaxed, it makes it even wider. And the wider the width here, the ones that are correctly classified in this particular classifier is very robust. But it also gives you a much bigger region of uncertain classification. Even this, though, is not sufficient to prevent something being confidently misclassified with this red point here way on the wrong side. So in this particular case, this support vector machine is not working totally well. Sticking to straight lines here seems to be very much limiting. So what you can do is you can actually embed this in a very high dimensional space and do the same thing and come up with a nonlinear classifier. What you do is you embed it in a very high dimensional space such that the distance between any 2 of these points is basically something similar to what we were doing with the partisan windows. So if you think of each fish giving off an odor, and you measure your distance to each fish by the intensity of this odor, you can represent these points in a very high dimensional space such that the distance between every point matches the distance you calculate using this odor. And if you do that, you can do the support vector machine linear separator in that high dimensional space, and then get a if you try to get a separator, then if you try to project that back to the original 2-dimensional space that you can see here, this divides the whole space into the regions that would be classified as red, the regions that would be classified as blue, and the no man's land in the middle. And here you can see that everything is well connected with using a very wide odor that spreads quite a distance. You can get a separator. It looks a lot like the partisan window separator we saw before. But this one is calculated a very different way in some that gives you some other guarantees about the robustness of this method. You can also tighten this odor and make it, if you don't like the errors, you can tighten the odor and get a more accurate separator. But you can see that this is beginning to suffer from overfitting because this line wiggles quite a bit. So it's not a very, this overfitting, by the way, is not a very precise concept, but This means that you're trying to fit the data set, your classifier, to the particular data set, with ignoring the fact that your future data won't be exactly like this. In this particular case, the set of blue points is still sort of connected, and the set of red, the area that would be classified as red points, is still sort of connected. The boundary is the one connected by these large squares. These are the guys that determine what the boundary is. The X's without any squares, this is in the interior of the region. And the ones with small circles around them are the ones in the no man's land between the blue and the red. And if you tighten this some more, oh, I guess I didn't show it. You get lots of little circles and the place breaks up. So that's it. That's what I wanted to say on classical methods. Now I would turn to a more learning approach, which is to try to do something that's very simple, sort of mathematically to set up, but that can manage to learn the difference. So, the simplest deep learning is very shallow. It's called a perceptron. And basically, the idea is to find a linear separator. I think I missed a slide in here. I'm not sure. Let's see, I think, yeah, here. So suppose this dates back to the 50s, really, but it's a very simple, it's the first computational unit that was inspired by the neurons in the nervous system in the brain. And it's called a perceptron, and it's a simple separator that is designed to work on data that is linearly separable. That is, there is a straight line that will separate the red from the blue. And the idea is this unit here, you have some number of inputs. In this particular case, 2 inputs here, this x1 and an x2, and plus a constant bias term that you can use to shift things around. And of course, this 2 is because I'm using 2-dimensional data. If I were using a 28 by 28 image, then I would have 784 of these x's going into this unit. It is combined, sent through some nonlinearity, and I get an output which is usually between 0 and 1 or -1 and 1. And the idea is, the reason why this is called a perceptron is in the way that it is trained. I have to determine the weights, these V's, these weights. So what the sum that goes into this nonlinear unit is the sum of x0 times v0 plus x1 times v1 plus x2 times v2. This is the inner product. And the output is then squashed so that it's always between like -1 and +1 or 0 and 1. In this particular case, it's -1 or +1. And in this particular case, the training is what makes this interesting. You simply cycle through, this is a snapshot of a Python program to actually carry this out. For each x is the sample, data sample, and y is the corresponding label. And y is either +1 or -1, and it's a class label for x. X is the sample data vector. You assume that this x0 is in there. You check if y inner product, the w here, I should have used v's. This is actually the v's. And that's what I'm trying to learn. What I'm trying to learn is the w. Remember, the x's here is the input data, and the y's are the input labels, and those are the two pieces that I'm given. The W is the unknown vector I'm trying to discover, which is initialized to 0. I missed, or to some random collection. If Y, if the sign, that is the plus or minus of the output, if the output mismatches the prediction of the input, so for instance, if V or W inner product X is positive and the corresponding Y is negative, then this inner product will be negative. You simply add a copy of the input to the weight vector. So this is the update rule. It's just a simple update rule. And you keep on cycling until you get no more mismatches. And it's kind of interesting that a simple algorithm like this actually is guaranteed to converge if the data has a linear separator. So to see, if I just show how this works in practice, you start with a random W, which goes to the origin in this case. And obviously, this is not the right W because you have blue points on both sides of the line and red points on both sides of the line. The slope of this is what is represented by this vector W. And you can go through the first step. You pick one of the blue points, and it obviously was a mismatch. So it would move this W. And after cycling through all of the 150 points, I drew the next W. That's the end of step 1, and this is now step 2. So this is what happens if you cycle through all of the training set, updating W every time. At the end of this one pass, W has been updated. You try it again, you update it some more, and the number of mismatches has gone down. And you keep on going until it cycles through. And I think in step 9, or step 10 rather, you finally reach a point where there are no mismatches anymore, and the method stops. And so this was the first in neural net inspired, neuron-inspired learning algorithm that dates from the 50s by, I think the guy's name was Rosenblatt. The next level was to add a layer. So what I showed before was a single layer. So you would have some number of inputs, a nonlinear layer, and the Y1 would be the output of the whole system. Well, you could chain these together and have this go into another layer that did something similar. And in fact, you could have multiple of these perceptrons sort of stacked together, either in parallel or in series. And this picture shows one hidden layer. There's one output layer, which is here, and one hidden layer, which are the two Ys. And obviously, you can increase the number of nodes within a hidden layer and the number of hidden layers. You could stack these up, and that's how you get to deep networks when you have less. You could have hundreds of layers here. The picture shows one hidden layer with two nodes, and they're called feature in modern parlance. I have an example where I used one hidden layer with 4 hidden nodes in here and tried it on the same, I think this is the fish, going back to the salmon and sea bass here. The salmon is these points over here on the left, and the sea bass are the points on the right. And I go through this layer. The nonlinearity, by the way, is 0.5 times 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10⁻⁷ × 10 in this point. This picture shows it as a step function, but actually, when you go to multiple layers, you replace the step function with a very smooth sigmoid function. It looks so that you turn this into you turn this square wave into a very smooth function so that you can actually take a derivative.
Can I ask a question about that slide?
Yeah.
So you show, you know, your raw data is your x's, right? And you're showing the same x1, 0, 1, 2 going into both y1 and y2. What is the difference of the data? Is that like you do lightness with one and the width with the other, or how are those separated? I'm not seeing that.
Well, the input data is going to, in this fully connected type of regime, each input coordinate is going to all of the hidden nodes. What's the difference is in the V. So now this V is a matrix. There's each one of these links has a different weight on them. And so the differentiation is that X1 is going to this Y1 with one weight and is going to Y2 with a different weight. And the learning process is to update these weights to improve to reduce an error function at the end. So each one of these.
But if
Yeah.
V is your unknown and that you're using the same inputs to calculate your unknown, wouldn't you get the same answer? That's my confusion.
Well, V is what you're trying to learn. If you start with V as a random, usually initialization is that V is going to be started with a bunch of random values, and W will be started with a bunch of random values. So the V on this link from X1 to Y1 will be different than the weight from X1 to Y2. And what that means is that when you update those weights, they'll go in different directions because what happens is that the learning process is very much like that perceptron learning process. You feed a sample in to this network, and then you measure the output error, and then you update each one of these weights to reduce the output error. And that's done by.
Why doesn't it converge to the same vector if it's the same inputs?
Because let's see, the fact that the weights are different means the change, you're computing a bunch of derivatives here. The update to this weight will be different than the update to this weight because they started in different, since they have different values, there are different points on this nonlinear, they give you different points on this nonlinear function here that is represented by this step function. So remembering that the step function is actually smoothed out. If, for instance, if the weight here, suppose that X1 times the weight here gives you a positive value for Y1, but the weight here gives you a negative value for Y2. When you want to change the weight to reduce the error function, you would end up, the weight on this link would move in an opposite direction to the weight on this function. And one has to go through the math.
Yeah, I understand that, but after you get to the very last step, I mean, you showed on the last slide that the V converges to one particular line until you have 0 errors. So how would it converge to a different line, or
Oh,
do we
that's-
not care about?
Yeah.
We care about taking the differences and figuring out W. Maybe that's what I'm confused.
Yeah, I mean, the W is also changing under you. So the error function in the preceding one is basically looking at the number of mismatches here at this particular node. Whereas here, the error function is more complicated. And so you end up, the change that you would make here would end up going to different, ends up going to a different local minimum. I mean, the local minimum in this particular node would be different from the local minimum from this particular node, because the weights, since the W's are very different, oops, the W's are very different, it would send the weights and the V's to different places. The error function is no longer, the error function that's being applied at this y1, y2 is no longer just a simple mismatch function, but it depends on the error function all the way at the bitter end here.
Okay, thank you. That helps.
Yeah. I mean, in order to really see, one has to look at the math that I wasn't really prepared to go through here, but I could show it at the end if people are interested. Hopefully the next example, more complicated example, will show this a little bit more. So since the output is not a step function, but is a smooth sigmoid function, you get, for each point in this region, you get a value that would be output by this network. And so the points here, the light brown and dark brown points or purple points are the salmon. The light ones are classified one way, and the dark ones are classified the other way. And the blue points, light blue are misclassified, and the dark blue are well classified sea bass. And here at the initialization, you can see that it's all wrong. But after convergence, the zero line is, I think, this one right here. And you can see everything to the left is classified as a salmon, and everything to the right is classified as a sea bass. And there are a few mistakes, so it's not perfect. And the others are other values. If you decide that, for instance, if you think that you're going to be able to catch more salmon and sea bass, you might move this threshold a little bit to the right. And the last curve gives you the convergence. So the blue is the measure of the error function, which is a sum of squares of the errors of the smoothed output. And the yellow line is a discrete, simply number of mismatches. The second example is running the same algorithm again with a different initialization, which happened to fail. So it's not guaranteed to work because everything is sort of random. You're doing a random initialization and maybe a random ordering in the data. And in fact, here, the initialization is shown here. The convergence, this line here is the separator. Whoops. Is the separator. And you can see that it didn't do a very good job. And so this is actually a symptom of the fact that there's some randomness here, and you might have to run it more than once to get a decent answer. Actually, this failure was actually rather rare. Most of the time it worked quite well. I just happened to catch this failure so I could capture it, but it was just chance. Even though it still shows a relatively small number of mismatches, but the error function didn't go down a lot. So that's what happens. So this is the result of a hand-coded Python without using any libraries other than the usual NumPy and Plotlive to generate these images. This was done by sort of just coding something from first principles. If you actually use a sort of a commercial grade neural network, you can get something more complicated. And this is where I was going to actually demonstrate this dynamically. This is not my demo. This is a demo I found on the web. Let's see, where's my Zoom window? Let's see. Okay, so you see this. So the idea here is, this is a network that is supposed to distinguish the 10 digits. So if I draw a 1, which would be like a vertical bar, this is the input. This is fed to 1, 2, 3, 4, 5, 6 hidden nodes in the next layer. This is fed to a downsampling layer where you take every, I think, 2 by 2 piece in the bigger layer and reduce it to do a sort of a dimensionality reduction. This is then goes to another layer in which things are combined in a different way. And these bars show what each unit in this layer, where it's getting its input from. So this is getting an input from 3 of the preceding layers. So this is a much more complicated network. And another downsampling. And then there's some fully connected layers. These guys are fully connected. So each pixel, each unit here is getting copies from all the preceding layers, of which there's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this is another fully connected layer. And then finally, there is a output layer with 10 outputs, each one representing 1 digit, 0 to 9. And this one, you can see there's only one that's bright. I don't know if you can see it, and the others are dark, so that it's pretty clear that it thinks that this is a 1, and it's pretty confident that it's not anything else. The second guess is a 0, but that's really minor. So this is an example of a more realistic network that you can actually play with. Let's see. We can use it to illustrate several points. So the thing that makes this distinctive is that this is not, what I showed in my preceding slides was a fully connected layer where every value in one layer was sent to every unit in the next layer. And this one doesn't have this property. This one is called a convolutional neural network, which was a revolutionary thing because it really made neural networks on images possible. So convolution means that each unit or pixel in this layer comes from only a small window in the layer below it. And the coefficients on this is common to all of these combinations. So you're actually running a sort of a convolution of a kernel across this with some set of weights. And if I click here, you can actually see the values. So the input image is black, where it says filter. Those are the weights of this particular convolution kernel. And you can see that it's sort of white under the F in the upper left corner and white in the lower right corner. And the others are some, what do you call it? Parameters. This is using the hyperbolic tangent as the non-linearity. And if you notice this filter, if I move to the next pixel over here, the filter is exactly the same. The input image is changed because now I'm at the below, I'm getting into the white area, but the filter is the same. And so the idea is to learn those coefficients. And then if I go to the next one, I get a different filter. This is almost the opposite filter. So to go back to the question you asked, why aren't these all filters the same? It's because of the random initialization. So each one of these six layers are getting, six units are getting a different filter, but this filter is common to all of the entries in this particular unit here. And the idea is to learn those. This is showing what happens after you've learned all of these weights. Then this one is a downsampling layer, and you can see what the values are and so on. So that's sort of the structure of this thing. And you can look at this one is, I'm not sure if it'll show I guess it doesn't show the value because it's off of the end there. So this is trained on a lot of handwritten digits. So it's trying to classify everything as a digit, 0 through 9. So if I draw a 4, let's see what it does. It actually thinks it's a 5. And then second chance is an 8. So you could see that it's not perfect. Suppose that I erase this part and draw a closed 4, see if that recognizes. Now it still thinks it's a 5. I'm not sure why. Let's try a 4 that's more centered. Now I get a 4. Okay. You can see that this is already showing one of the big issues with neural networks in general, which is that they tend to be brittle. So this 4 here is recognized as a 4, but the 4 that I had before was misrepresented as a 5, and I don't think there is anybody in the world who would not recognize this as a sort of a 4. If you had to classify this as a digit, this time it was classified correctly as a 4. I'm not even sure I could reproduce the five, 7. This is interesting. Now it doesn't even think 4 is a very it doesn't even think 4 is not even the second choice. So you can so this gives you an idea of the power and also the limitations of this neural network. So first I should say, why is a convolutional neural network such a advance in machine learning? And the answer is that in an image, if you think of an image with a bunch of objects in it, and you're trying to recognize the objects, it really should not matter whether that object appears in the upper left corner or the lower right corner of the image. It should be treated the same. And that's what the neural network attempts to do. If I draw a 0 in this particular place, which it doesn't limit. Because if I draw a 0, let's see what it does. A 0 in this corner should be treated the same as a 0 in this corner. I don't know if it is because the 0 is kind of rough. Obviously, this neural network is not actually doing very well. In principle, a convolution should factor out the fact that the location in the image often is irrelevant in recognizing an object. So if I draw a 1 over here, should be treated the same as a 1 over here. So that's the power of the convolutional neural network. And obviously, in order to make this more robust, I would have to jazz this up. And typically that's done by adding a lot more layers. And you also see the downside of neural networks in this example because of the brittleness of, this is brittle in two senses. One is anything that I draw, it only knows things that it saw in the training data. So if I draw something that it never saw in the training data, it'll try to classify it as a digit, because the digits are the only things that it's ever seen. And so if I draw something that it was not in the training data, it will coerce it into what it has seen. But that's not the real problem, is the fact that if I draw something as I had at the beginning, and make a change here, let's see, if make a small change, let's see if I make a small change to this input, it can make a big change in the output. So without this little cross thing, it thinks it's a 1. As soon as I put in this little cross thing, it all of a sudden gets fooled into thinking this is something completely different. And this is still a problem in real live sort of production neural nets. It's sometimes not obvious to know what change one should put in there to make this, to change the classification, but this is a common problem, that these neural nets tend to be brittle. And then the third thing that you might observe from this demo is the fact that unlike the classical classification methods I talked about earlier, in this particular case, you have no idea why does it think that this is an 8. If you go back to the probabilistic method or the Parson window method or even the support vector machine method, and you came up with a classification of 8, you could go back and figure out, well, what features did it pick up on to decide that it was an 8 or that it decided it was a salmon. You can backtrack and figure out, well, what was it about the input that gave you that classification? Whereas here, it's going through all sorts of mishmash with these layers, and you have no idea what in this thing is making it think that it's an 8. It's obviously not looking at the image as a whole, because an 8 has 2 loops, an enclosed space, the 2 circles that touch each other, and here there are no circles, no enclosed space or anything. So obviously the features that are using to decide that it's an 8 are completely different from what you and me would use. So those are the 3 downsides of this: the brittleness, the lack of explainability, and the fact that what it learns depends really on the data that you supply. So if you think about it, if the data that I supplied was biased toward ones and twos and had very few eights in it, it would have learned something that wouldn't have a lot of trouble identifying eights. And this is actually a serious problem. So it has a lot of power, but it also has a lot of issues. So let me go back to the slides. So let's see if I can. So I went through this demo. This was a case of a 4 that it thought was a 6. So anyway, that sort of gives you an illustration of a convolutional neural net, which is probably the workhorse net that's used today in image processing. So this gives you a real life example of this brittleness, which could actually show why it's a serious issue. So this is a paper that appeared recently in which they took the image of a stop sign and recognizes it as a stop sign, but by shining a carefully constructed illumination to the stop sign, for which they needed to have access. I believe they needed to have access to the network. By shining a special illumination, they managed to convince the neural network that this was a speed limit 30 sign. So you can imagine that this kind of misclassification would be a serious problem in a self-driving car. And every so often you see a paper appear in which they show one variation on this theme from another. In an earlier paper, they took this stop sign and actually pasted duct tape on it in a special way and convinced it that it was a speed limit 45 sign. This one was new because they didn't actually modify the sign at all. They just modified the way it was illuminated. And the other issue is the bias in the data. So I mentioned in the preceding one, if you didn't have any eights or had very few eights in the data, the neural network would learn to distinguish, they say, ones and twos very well, but couldn't figure out what to do with eights. And this is a serious problem that is still haunting the big companies. So this was an article that appeared just earlier this month in which some machine learning algorithm at Facebook sort of mislabeled this image as a primate and caused a lot of grief. And it's not the first time this has happened, and it's almost surely not going to be the last. And usually this is a result of bias in the training data. So if you think in terms of face recognition, if you have very few people in a particular racial category, like for instance, in China, they do a lot of face recognition, and one would guess that most of the faces they use for training are Chinese. So if you have a Westerner appear in there, it probably doesn't do a good job in recognizing such a person. Even people have this suffer. As a Western Caucasian white person, I still have trouble recognizing, some Oriental faces from one another. And so it's not actually something that is limited to machine learning. I think actually people suffer from this as well. But it's more serious when it's in machine learning and it's sort of embedded into the system when by changing the data used to train the data, you could avoid it. So here are some examples of handwritten digits that were used to train, that presumably were used to train that earlier network I was showing you. This is the standard data set that comes from MNIST. If you look up MNIST on the Google, you'll find this set of data. And these are images. Basically, the input data to the network is simply to string out all of the pixels into a single vector, to stack them up, and that becomes your input data to the image. And so this particular data is relatively easy to factor. So if you actually look at the data, this is sort of a color diagram of this matrix of input data. So each row represents a new sample. And each row is, I think in this data, 784 elements long, because that's how many pixels you have in an image. And the first column is the label, actually. And this is only 3 digits, 0, 8, and 9. I think this is 8, 9, and 0. Right, yeah, 8. First 1,000 8s, 1,000 9s, and 1,000 zeros. And you can see that from this, you can't tell anything. But if you think of this, so this is a new machine learning paradigm, which is dimensionality reduction. So one of the things that one would like to do is try to figure out if there's any pattern in this data. I don't think anybody here can visualize space in 784 dimensions, but you could visualize in 2 or 3 dimensions. So can you project this 784 down to 3 dimensions or 2 dimensions in which you can actually visualize and see if there are any patterns? Principal component analysis is the simplest way of doing that. And it basically tries to find the direction of maximal variance and use that as your first dimension. And then the next dimension is in the direction of maximal variance and what's left over. Maximal variance means maximal variation. So if you do that in 2 dimensions, you see this. Black is 0, red is 8, and blue is 9. And you can see that, in fact, they're separated in these 2 dimensions. You can see the zeros are actually somewhat separate from the 8s and the 9s, and they're sort of bunched together. And if you do 3 dimensions, it's even more so. And so you can actually tell that you could actually separate these digits without using this fancy neural network that I was showing before. You might actually be able to use a more classical method that might actually do a halfway decent job. Like here, you could fit a hyperplane between or a plane between the blue and the red and separate the 9s from everything else. There would be limitations because the neural network hopefully does a better job in handling the case where your 9s might vary from one corner, might move around. The convolutional nature might actually help you avoid some of these translation issues. But this actually tells you that, in fact, this data should be relatively easy to write a classifier for. So that gives you a simple introduction to the standard feed-forward neural networks. I should go back here just to tell you, this is called a feed-forward neural network because it contains no memory. It's all, the data is fed through and it goes from left to right. And the training process starts from the right. You update, you take each sample, you measure the discrepancy with the label, which is the output of this node right here, it should be a Z, it was cut off. You update the W weights based on this output, and then they propagate that back and get some updates to the V's. And if you look at the math, you can discover that the formulas for these updates is very straightforward. And you also look at the math and discover that if the weights are randomly initialized, they'll all go in different directions and will tend to differentiate themselves. And so if you look at this, for instance, this picture, the weights that go from the input here to this node will be different than the weights that go to the next node, from here to the next node. And that's just a result of the random initialization. If you were to initialize V to a constant, then you wouldn't see that differentiation and you would not get a good answer. So there are variations. So this is an example of principal component analysis. I can't really say a lot about neural networks in general, but I can give some examples of more recent neural networks that are useful. And one is called a variational autoencoder, or just an autoencoder, depending on the details. So this is a simple version. It's sort of a dimensionality reduction in a more nonlinear way. So the principal component analysis is only looking at the direction of maximal variation. It doesn't tell you whether that direction is actually a useful direction as far as classifying or as far as reproducing the output. If you think a lot of high dimensional data, like those digits, even though they're in, if you go back here, even though they're in 784 dimensional space, actually they sit in a much lower dimensional space. You can already see that because each row represents a sample vector. Remember, each row is 784 elements long. You notice that there's a lot of white space down this first column here. This white space are all zeros. So you can already see that these digits don't live in all of 784 space. They actually live in a smaller dimension because all of these elements, they all have zeros in their first, say, 100 plus elements, and the last 50 elements on this side are also all zero. And that's a consequence of the fact that you write the digits in the middle of the square, not in the corners. So you can already see that these digits live in a manifold that doesn't occupy the entire space, but this manifold is probably very nonlinear. So variational autoencoders are a neural network way of trying to discover what those manifolds are. So the way it works is you feed the inputs over here. It goes through an encoder to a much smaller set of numbers, which then goes through a decoder to get the output, which should match the input. And the whole idea is to learn weights inside the encoder and the decoder so that you can reproduce the output. The output matches the input. And if you get the weights right and the input matches what happens if you pass the input through the encoder E and then through the decoder D. If it's equal to X, then you actually have a lossless encoding. So instead of having 1 to 7 sitting in 7-dimensional space, you can represent this sample with only 3 numbers here. So if I put in 1, 2, and 3 here, I would get a 7-dimensional output that would exactly match 7-dimensional input that I have here. And therefore I can represent this 7-dimensional data sample with only 3 numbers, the ones that appear here. And what are those 3 numbers? It would be whatever the encoder spits out. And that way I could reproduce new samples here by simply feeding in new 3 vectors here. And that would give me some samples here that look like input vectors. And this is used for various things, like it could be used to reduce the dimensionality of the input to something that would be more manageable, that then I could feed to a classifier network. So you see that this is an unsupervised process because there are no labels. So I'm just trying to reproduce the input by using as few samples here as possible. So you can think of the input maybe as 700 dimension or 1,000 dimension or 10,000 dimensional. And here you might, and in the middle, you might have like 300. I should say that a lot of useful information can be done when I've done Google searches online. A lot of times I've ended up at this towardatascience.com. There are lots of articles. It's a bunch of small, short articles. Each one gives you a nice introduction to certain data science concepts, which you probably find useful. So this is one example, and there are variations on this. There's another more complicated version of this where you not only try to learn this small encoding E of X, but also a mean and variance of this data to try to make this more robust to variations in the input, so that implicitly you encode not only the input data, but the input data plus some variation to account for the fact, you want to account for the fact that the input data will not exactly match future data that you might see once you deploy whatever system you have. And the another powerful technique that's been generated is what's called a generative adversarial network, or GAN. And this is another one where you have 2 pieces that try to compete against each other. And this one you start with a set of real data. So you have a large set of real data. And what you want to do is create a generator that would take some random input vector, which would be Gaussian noise, and generate examples that look like the real thing. And then in order to make this happen, you also create a discriminator that tries to tell whether it's a real example or a fake example that came from the generated generator. So suppose that you start this initialization, you can train the discriminator to discriminate between real examples and the generated examples. If the generator is just random at the beginning, then that should be easy. The real example will probably be a sharp image, and the generated example will probably just random noise. So it should be easy to discriminate. Once the discriminator does a good job of discriminating, you then can update the weights inside the generator model. Remembering the generator model and the discriminator model, both neural networks, to try to reduce the discriminator error. That is to try to, the goal of the generator, the loss function that you use to update it is how well the discriminator is deciding that it's fake. So the generator is trying to fool the discriminator into thinking that this generated example is real. And so you update the weights in the generator to the loss function is basically the opposite here the loss function is to maximize the number of times a generated example is considered a real example by the discriminator. And so you go through this back and forth until at the end, the generator does such a good job that the discriminator can't tell, basically treats all of these generated examples as real. So this is the simplest version of a GAN, and this link at the bottom is another website that has some nice articles on some of these things. And to give an idea of how well these GANs work, this is an illustration showing the progress in generating fake faces by this method. In fact, this is fairly recent. In 2014, you could generate faces that look like faces, but were pretty fuzzy. And as time goes along, they got better and better. And now they look pretty sharp. If you think in terms of, instead of faces, you think in terms of images of other things, you can tell that this has a lot of power to it, both good and bad. The downside of GANs is they're hard to train because of the fact that you have these competing goals. You can fall into ruts where the generator can collapse into generating always the same picture that the discriminator treats as real, but doesn't actually give you anything useful. So if you think in terms of, if the generator just picked one of the real examples and simply spat it out, the discriminator would never be able to distinguish it, but the output would not be of any use. So the training process is more complex in this case. So that's a survey of some supervised algorithms and some deep learning algorithms. I could end with some unsupervised algorithms. We've already saw dimensionality reduction. For unsupervised algorithms, the more classic ones are, the classic methods are clustering as opposed to dimensionality reduction. So I mentioned with unsupervised algorithms, you either want to reduce the dimension or you want to find patterns or groupings. That's what the latter is what clustering does. And one of the popular algorithms here is the simple-minded one, which basically follows a simple paradigm. You start with an initial random assignment to groups. You then compute the center for each group or hub, and then you regroup the data. And you repeat until it looks good. Expectation maximization is good because you try to fit some probability distribution. So you posit that the data was generated by some probability distribution, and you want to find the parameters. Like if you have like two Gaussians that generated the data, can you figure out what the means and standard deviation of the two Gaussians? So here, along the bottom here, I have a bunch of sample points that are black stars. And I want to find two Gaussians that would generate these. Either each black star was either generated by one Gaussian or another second Gaussian, and I want to find out what those two Gaussians are. The red dots are the centers of where I think the Gaussians are. So I think the Gaussians are, one is peaked here and one is peaked there. And if I add the two together, I get the big purple curve. And I can go through this iteration to try to figure out what these Gaussians are. And if you follow the algorithm that after 12 steps, I've managed to separate them into two separate Gaussians with a center, one here and one here. And I have a standard deviation, which is the width of this curve up here. And I can just go through this again. backwards. So this is in 1 dimension. You can do the same in 2 dimensions. I have a bunch of black points, and I want to separate them into 2 Gaussians. And the big blue diamonds are the centers of where I think these Gaussians are. And if I go, this process works in multiple dimensions. And that basically, a Gaussian is probably not a good model here because these points look like they're all sort of lined up in a line. So that's probably not the best model, but this is what happens in this case. And if you do it on a ring of points, it tends to spread them out over the points. So here I have a donut of points, and if I follow the let this go, it generally tends to spread out until after, what is it, 9 steps, I have this situation, which is probably not the best representation, but it is enough to tell me that these blue points do give me a sort of a rough sketch of how all the little black points are distributed. And to go back to the fishes that you can imagine doing this on the fish example I started with. So in k-means, is basically following a similar algorithm. This is what happens if I don't know. So you have to imagine that now this is an unlabeled data. So I don't know which point is a salmon and which point is a sea bass. I'm just trying to see whether they're grouped, whether it's just one big blob of fishes or if there's more than one type of fish in this data set. I don't know how many types of fishes are. So in this particular case, I asked for 4, and I get 4 clusters. I get the light tan here, the beige here, the reddish here, purple here, and the sort of the green ones here. The circles are the centers of each of these 4 clusters. You notice there are 4 circles. And I can do this again. And the k-means has this problem that if you do random initialization, you'll get a different answer. So this has a different set of, a different split. So if you look at this particular point right there, it's grouped with the set above in this one, but it's grouped with the set below in this one. So there's some non-determinacy in this k-means, depending on how it's initialized. And if I do 2 clusters, because I happen to know that there are only 2 kinds of fish, it's possible I could get a very good separation like I have here, with all the salmon colored purple and all the sea bass colored red, more or less. Or it could be very bad, like here, where the separator is actually more horizontal. Everything above this line is classified as red or sea bass, and everything below is classified as the other one. And I shouldn't say classified as sea bass because it's just in cluster 1 and cluster 2. I don't know what the labels are. So one has to, this shows, yeah, clustering can do quite well, but you have to be careful how you interpret it. Let's see. So I think I've reached the end of what I wanted to say. I tried to illustrate a whole bunch of machine learning methods sort of pictorially without getting into any of the math. Or should answer some of those questions, like the question about why they go differently. But would have to actually look at the formulas. Turns out the updates, if you use a smooth nonlinearity, then you can compute derivatives or gradients in this case. And it turns out the gradients that are not constant. They have lots of variation in them. And if you start with random weights. The grading, the change you want to make to any weight depends on the weights in the preceding layer or the layer after it, and the values of the input values. And since there are lots of differences there, the weights on the different edges will go off in different directions.
Yeah, you actually answered that question very well when you went
Yeah.
back to it. I think I get it, which is awesome. Thank you.
Okay. So I just tried to stick to pictures. I went through a few classical methods that had the advantage of being explainable, and some deep learning methods that can capture a lot of hidden nonlinearities that that are embedded within the data. I alluded to some issues with deep learning methods, especially with ethical issues that are a result of bias in the data or in the statistical models. I didn't say anything about other issues with the data regarding like privacy or consent to the collected data. For instance, even if you don't have access to the data, if you're given the model that is this neural network, could you use that to recover some private information from the data? I said something about explainability. The computational cost is something I haven't talked about. If you think in terms of the neural networks, there are lots of little units. Each one is doing a simple computation. The power comes from stacking them together. But you could think that easily imagine that those can be distributed onto, each unit could be distributed onto a different processor, or handled at least in parallel. And that immediately lends itself, but each unit can be done in parallel, but the computation involved in that unit is very simple. And so it turns out to be a natural for distributing it onto graphical processing units, which are designed to do a simple computation a lot of times in parallel. And that's why GPUs are very popular in this business. And finally, there are lots of things I could say about other things that I haven't had a chance to talk about. So all the methods that I've talked about are treating data as if they are elements in high dimensional Euclidean space, which is a fancy way of saying that each data sample is a vector of numbers, a long set of numbers. But that's not always the case. So if you have things that are not numbers, like categories in the data, there are other methods like random forest, decision trees, which can come into play a role. There's reinforcement learning, which is another learning method that depends on sampling the input space, but in a much more limited way. Sometimes you have, sometimes you want to, anomaly detection is where you have a good model for one class, but a very poor model for the other class. So you can think of the method the example I would have in mind is like breaking into a computer system. If you look at the pattern of access to files, you can get a good model of the usual pattern for accessing files because you can observe what users do day to day. But a break-in is going to be something different, and you have no idea what method they're going to use to try to break in. It could be through the operating system, through a web page, through some other method. You have no model for that. You're just looking for something that's different from the usual. And that would be anomaly detection. And then there are more complicated neural networks that I haven't had a chance to look at, sort of recurrent neural networks or long short-term memory networks that actually store a state. These are useful if you're looking at time series where the data, the order in which data is presented makes a difference, like stock market history. where you want to, you're given the data, say up to a certain point, and then you want to predict what's going to happen tomorrow, or the weather. You know, is it going to rain tomorrow, depending on whether it's raining today? And there you need some memory to store it within the network. You need something to sort of encode the fact that you encode the history. So that is all I have. I'd be happy to answer any other questions, or at least entertain the questions. Whether I can answer them or not is another question. So thank you.
When it comes to the application of this stuff, is it mostly like, you know, the person working on it, you know, they encounter a novel problem, and then they just sort of have to, you know, think back to their toolkit of all of these methods that they know, to, you know, decide how to best look at it?
Yeah, I guess one popular paradigm is, like, this is one that we use, people have used like in medical imaging. There's been a lot of work in neural networks to classify regular images of actual outdoor scenes or indoor scenes of the taken of people or streets or whatever. And there are a lot of networks. A lot of these neural networks have been published, which means they've actually published all the weights in a form that you could actually run the network on your images. So a lot of times what happens is that they take one of these published networks for a similar problem and apply it to the new situation. So for medical imaging, they would take these networks, start with networks like ImageNet that was trained on regular photographs that you would take while you go to the park, and then train them on X-rays where maybe only a few of the layers are allowed to vary, because a lot of the early layers are picking up low-level features that are common to any kind of image, like edges and closed curves and whatnot. And so a lot of times what happens, these networks are designed by taking an existing, or have gotten to the point where they take an existing network and modify it to suit the new situation. There's also the issue, a lot of this is also, each new kind of data set also has its own set of noise issues, like X-rays. There are lots of issues with anomalous X-rays that are not taken in the right orientation, or have been misclassified. I was looking at this data of chest X-rays, and occasionally you see an X-ray of an infant, which is very different from an adult. And so you have to throw those out. And so they use, that leads itself to anomaly detection to eliminate X-rays that don't fit the pattern that we're looking for. So every new situation requires a little bit of homegrown design, but they almost always start with some existing network as a starting point, in order to make this sure that it works. Does that answer the question? I hope.
Yes, it does. Thank you.
Yeah. Anybody else have a question? Well, I hope this was interesting. This was probably a lot more academic than Knight's talk, I would think. But if you have any further questions, I'd be happy to answer them offline or.
It was extremely interesting talk and just put it at a level for me who knows nothing about machine learning to really kind of pick up on the different methodologies and kind of see how it's working. So thank you. I thought it was fantastic.
Okay, thank you.
Well, thank you, Dan. That was great.
Okay.
Thank you, everybody, for being here, for showing up to the seminar. Have a good weekend.
Okay, well, thank you for listening and thank you for inviting me.
You bet.